Good morning. Welcome to the first talk of this day. It's a pleasure to chair the session where we have Professor Roger Blandford giving a talk. Professor Blandford is at Stanford. He is the professor of physics, particle physics and astronomy, astroparticle physics. And I would also like to mention he's the founding director of CAIPAC at Stanford. And about his science, I would just say in the Indian lingo, he would be called the Dada of black hole astrophysics. And so here's Roger.
Okay, well, thank you very much for the kind invitation. It's truly a great honor and a pleasure to be here, an honor to help celebrate the centenary of quantum mechanics, and a pleasure as I always have such a great time, and I never know what's going to happen next when I come to Bangalore. So, and congratulations to Rajesh and everybody on making a truly wonderful institution here, ICTS. So, physics progressed from classical mechanics to quantum mechanics, as everyone here knows, a sequence of amazing insights and inexcusable diversions. Newton, Leibniz, Lagrange, Hamilton, Faraday, Maxwell, Lorentz, Planck, Einstein, Bohr, they all made these enormous conceptual and technical steps along the road, and then here we're celebrating so many people, but I think for many of us, Heisenberg, Dirac, Fermi, Pauli, followed by Schrödinger, are brought in this completely revolutionary way of thinking about physics. And then that quickly evolved into atomic physics, nuclear physics, elementary particle physics, quantum electrodynamics, quantum field theory, but beyond. And he did this as theory, experiment, and technology, as we've heard, particularly in this meeting. But in parallel to all of this development, with which most of this meeting has been about, astronomy was also embarking on a glorious century of discovery. It was changing from the fixation on classical mechanics and taxonomy to essentially astrophysics and observational cosmology. For example, in 1919, Mount Wilson made its first observations. In the 1930s, radio astronomy got its start. In the 60s, X-ray astronomy. In the 70s, modern infrared astronomy, ultraviolet astronomy, gamma ray astronomy, and now we've got neutrinos and gravitational waves. If you like, a focus on stars moved inwards, or to smaller scale, if you like, to white dwarfs, neutron stars, black holes, extrasolar planets, and then outwards to galaxies and the expanding universe with the dark matter, dark energy, and so on. So it's been a century of astronomy too, as much as that of quantum mechanics. And they have evolved in ways that are strongly entangled. Especially, I think one of the links actually, which I'll come back to, is cosmic rays. Now, so we've developed a sort of understanding of physics that has provided us with the tools for astrophysicists to shamelessly use and interpret the observations. So they've been consumers in some sense of this great developments in physics. But they've also been contributors, and they've begotten new fields of physics, for example. And cosmology and black holes took fundamental physics out of the laboratory. And perhaps an unsung part of this is that the quantum mechanical technology is really what enabled the revolutionary detectors that opened up multi-wavelength and multi-messenger studies of all astrophysical sources and beyond. So in this talk, I'll try to sort of outline this symbiotic relationship between quantum mechanics and astrophysics and cosmology. And I'll do it in a way that I am conscious of the fact that I'll be abusing history, partly through ignorance, but also because I'm in a hurry and I've only got now 46 minutes and 4 seconds to tell you about all of this. And also, Rajesh asked that I survey the entire quantum mechanical universe in 4 dimensions from an astronomical perspective. So as a consequence, although my width might be a gigaparsec, the depth of this presentation will be measured in nanometers. And there'll be no equations, no details, and I'll just be one long list of discoveries and ideas. And I try to organize this by atomic astrophysics, nuclear astrophysics, particle astrophysics, and cosmology. And then I'll just conclude with somewhat, perhaps in a self-centered way, with three topics that if I get time to talk to them a little bit, I'll just introduce them, that I'm personally working on and interested in about at the moment. And they're ones where I think the way forward is intrinsically quantum mechanical, but it's new quantum mechanics that's needed. Okay, so let me move on to the next slide, just to draw for the sort of resolute physicists here what has actually happened to astronomy. In the old days, it was just one octave observed with our eyes, seen through better and better telescopes, so you've got one octave there. Now we've got 140 octaves, more or less. The whole electromagnetic spectrum being opened up, gravitational radiation, cosmic rays, they've been with us for a long time, neutrinos and so on, and going from zepto-electron volts, if you like, to zeta-electron volts, and many ways of measuring this and doing this. You know, we're given all this huge expansion in scope. Even third-rate scientists can make discoveries, and my colleagues are first-rate scientists, and so it's not surprising there's been an explosion. I said I'd start with atomic astrophysics. Here, again, in the 19th century, there were Fraunhofer lines, about 1,000 of them or so, and helium I think in 1868 was discovered. I actually only just realized it was actually in India that the spectrum was taken, that where helium was found. And of course, here's Annie Jump Cannon and others, and many others did amazing observational work classifying the lines, but this was done she and her successors did it in the context of a developing understanding of the atomic physics that was going into lines and making the identifications and so on. And you can sort of see, this is the mid-19th century classification. It was sort of alphabetical, but when it got organized by temperature and then much else besides, it now became, you can see what happened, of course, and then there's the famous sort of Hertzsprung-Russell diagram, which tells you most of the stars lie on this so-called main sequence, which is this sort of more or less maps the mass, going from high mass up here to low mass down there, and that's where you spend most of your time as a star, and temperature this way and luminosity that way, and a lot of detail. Of course, there are about 7 more spectral types that are introduced, and these are subdivided and so on. And this was all enabled by atomic astrophysics. And now, of course, in solar physics, I think there are, 30,000 lines, I think, in the solar spectrum. It's always been true that half of them are understood and identified, and the other half are a work in progress, and that will continue. As we're in the Chandrasekhar Auditorium, I'll mention Chandra, who did heroic work, firstly developing the techniques of radiative transfer, but also understanding the atomic physics of the negative helium ion. And so he contributed to that here. And so we've got these stars here, and of course I'm going to astronomy here. These are the ones that live fast and die young, and those are the ones that have got another 100 billion years to live. So let's move on. The new thing that's happening, of course, with the brilliantly successful James Webb Space Telescope is extending all of this into looking in exoplanets, looking in their spectra, both in emission and in transmission. And a lot of the sort of, at least, the focus of this is just to understand what's going on, but there's a large popular interest, if you like, in the search for biosignatures, which is turning out to be a very interesting, but also a much more complicated business. It's easy to say, there's water or there's carbon dioxide or ammonia or phosphine or what, you take your pick, and you say, therefore, there's somebody there, we can say, take me to your leader or something. But in fact, of course, most of these molecules which can be detected can have quite inorganic origins, and we're learning a lot more about it. And again, this is a quantum mechanical exercise. It's applied quantum mechanics for sure, but it's been a heroic business, and it's a work very much in progress. So this is making ammonia doesn't actually require cows. So it's just other things that are going on, and so it takes you obviously into astrophysics and many questions of what the physical conditions are like in all of these extrasolar environments. Okay, so going out into interstellar space, then this again has been developing largely through radio and millimeter astronomy. There are many unique molecules. Many of them are found on interstellar dust, interstellar grains, and here's one here, cyanopyrene, a longer name. It's a polycyclic aromatic hydrocarbon, things like that. These are sort of completely exotic things for a laboratory chemist. These are completely exotic things, and a lot of the atomic physics, molecular physics, of them has to be understood from direct calculation. But it works, and so it's happening fine. The diffuse interstellar bands, they now, the Raman spectroscopy that we heard yesterday from Rajaram, that is also now a feature of trying to understand that. This is coming up directly in that. I'll say a little bit more about this later on. A recent thing that relates, again, something I might finish off with, is the discovery of the first chiral molecule. It's only seen in racemic form in interstellar space, but this is the first genuinely chiral model that's been positively identified. That's been a recent thing in the last year or so. Okay, I think that's probably what I wanted to say about. Oh, yeah, I'm going to say one more thing. Yes, even humble molecular hydrogen, you might think, was very well understood, but that turned out not to be the case, because in the totally exotic conditions in the very early universe, where there are no grains and so on, there are features that are actually important in terms of interpreting the observations that are only understood in recent years. Again, molecular astrophysics, using the principles of quantum mechanics. Moving onwards, just this is sort of potted history here to stars. It was in the 19th century, stars were powered by gravitation. They lasted millions of years. What could go wrong with that? Unfortunately, they had to last for billions of years, as was quickly discovered, and that was a big problem. And so nuclear physics was invented, and nuclear physics, through various heroes along the way. Eddington was probably the first to do this, and he sort of said that the sun was powered by nuclear reactions. He had a bit of a problem because he understood about the Coulomb barrier, but didn't yet understand. This is about 1920. Didn't yet understand about tunneling, which required Gamow. But now we have a sort of theory of nuclear fusion that takes hydrogen to helium. There are actually 3 of these chains that do it. This is just one of them shown schematically here. The big thing is the weak interaction that takes 1 billion years or so to start off with. And then when the stars get hotter, Hans Bethe, I had a great privilege of spending some time talking with him. In fact, I used to boast that I knew Hans Bethe as a young man because I attended his 75th birthday party, and he was, of course, a ball of fire. As I'm just 75 myself, it is a somewhat poignant remark to make. But anyway, but he also involved with the so-called CNO chain, where there's 3 or 4 of those 2 cycles there. Here's just one of them. They're sort of complicated reactions for which the necessary reaction rates were measured and applied to give a good understanding of nuclear energy generation in these stars. And this is fine until you run out of fuel. And at that point, if you're a low mass star like the sun, you're going to evolve through a red giant phase to make a white dwarf. But a high mass star has the option of going into neutron stars and black holes and so on. Again, this is all quantum mechanics. The stories that we tell are all essentially quantum mechanical. in their origin. Neutrinos, of course, are a big part. I'll come back to that in a moment. A big part of this, and we can, we'll say a little bit more about that in a moment. But again, this was a very rapid application of quantum mechanics, in this case applied to atomic nuclei. An even more dramatic application, equally dramatic application, was to Big Bang nucleosynthesis. If we look at the early application, this was George Gamow, of course, who was famous for talking about the hot Big Bang, and the contrary version was the sort of steady state theory that was championed by my erstwhile boss, another brilliant man, Fred Hoyle, and he actually gave the name Big Bang. He gave the name Big Bang, but he meant it more or less sarcastically. But turns out there was a clear choice that was made, and then we now have a very good description of how helium is formed in the early universe, given generic early conditions. This is the sort of cycle of reactions here. I'm not going to go through any of this. And basically, it takes hydrogen. There's some neutrons around. The extra neutrons make some deuterium here. It's a very careful, it's a very straightforward and generic calculation. You build up the deuterium abundance when you can just get some of them to react to make the alpha particles here. This is the helium, and so most of the neutrons go into helium. And this all happens in about 5 minutes in the early universe. Now, to those who work in quantum cosmology, that's an insufferably long time, but for those who are astronomers, it's remarkably short. Okay, there's a little bit of deuterium and lithium left over, but as famously well known, there's no nuclei with stable nuclei with atomic weights of 5 or 8, which is what you need to take the story further on. So this was a brilliant way of explaining the whole periodic table all the way up to helium, which is all is taught nowadays anyway by physicists. So, okay, so the next steps were taken in the 1940s and especially 1950s, culminating in a paper by Burbage, Fowler, and Hoyle. Hoyle again, and Hoyle had previously made the bold conjecture that there was a resonant state, an excited state of carbon, which will enable beryllium essentially to build up to the so-called triple alpha process to make this carbon, enough of it to burn the helium to get it into carbon under conditions which were not present in the early universe but could be present in stars. So this is the so-called triple alpha process. Again, some deep understanding of nuclear physics to say this has happened, and then of course they went to do experiments and they did find precisely what was predicted. It was brilliant, and it's a very sort of contrived solution if you just think about it. And this, of course, has caught the attention of those who like intelligent design or the anthropic principle. And I'm not going to take sides here. I believe in religious freedom, and I think one should respect all of these principles. Any rate, what they did, this was sort of, in some sense, a culmination of what they and others have been thinking, but it added a huge amount more to the picture of the building up of the chemical elements in stars, and they identified generic processes. It's all much more complicated than this. There's a sort of P process, which is when you build up the proton-rich nuclei. There's the R process, which is rapid neutron capture, when you build up the nuclei that have got lots of neutrons, and you do this faster than the beta decays. Now, of course, beta decays happens on a range of timescales, so this is just a sort of general thought as to what actually happens here. And this is supposed to happen in the supernovae of neutron stars, of massive stars, excuse me, leading to neutron stars and black holes. But now we know that this R process, as was conjectured, and there's now good demonstrations, extremely good demonstrations from the binary neutron star merger that was seen by gravitational waves. There's now good demonstration that this is a source also of these R process elements. Sometimes this is called a kilonova, and And this is just one little bit of the R process. This is the whole periodic table, whole charge of the nuclides, excuse me. But this is one little bit, and it shows the processes that can happen. And then which happens depends on coupling the nuclear physics with the astrophysics of the sites. And then the third thing is the S process. There are other processes, but the S process, which is when the opposite is true, is when the beta decays largely happen before the next neutron capture. And this happens in evolving lower mass stars. The sun will do its bit eventually. And if one looks at the evolving high mass stars, then you get this again is an oversimplification, but you get these sort of burning shells one on top of the other. And this is the environment where all this nuclear astrophysics is prosecuting. Let me move on. So this is, again, I'm not going to go, this is the chart of the periodic table of the elements. And if you want to know where you come from, this gives you a little key here from the Big Bang. Cosmic rays, of course, make these, a lot of the lithium, beryllium, boron are made from spallation of cosmic rays. There's the merging neutron stars I just told you about, and the exploding massive stars, the supernovae. There's the S process and the dying low mass stars. And then another type of supernova is genuinely a nuclear reaction, which is white dwarf. There are two versions of this. These are the so-called type 1a supernovae. And these white dwarfs, they can either be in a binary or they can be near their so-called Chandrasekhar limit. And they can also give you the supernovae that are used for measuring the universe particularly, but they also create some of these elements here, the ones in blue here, and anyway, so let's, yeah, so those are, again, one can't defend all of this completely. There are details and so on, but as a work in progress, there's been enormous development over the past 4 or 5 years in advancing this story. Okay, let's go on now to neutrinos, another sort of entangled topic between astronomy and physics. Again, I'm not, you know all of this, so I'm just going to sort of supervise. There are the solar and the supernova neutrinos in sort of MeV energies. The solar neutrino, there's the solar neutrino problem, and that was, I witnessed this sort of more or less from a safe distance, but reasonably close to see what was going on. And Ray Davis especially, and others were trying to do, but Ray Davis in the Homestead mine was looking for the solar neutrinos, and eventually he found them. We were able to detect them using what you call dry cleaning fluid, it's carbon tetrachloride, and perchloroethylene, and heroic experiment. And I just say, just watching from a safe distance, I was always an immense admirer because he wasn't quite getting the predicted rate. And John McCall and many others had actually been able to use nuclear astrophysics to calculate with confidence what the rate of neutrinos ought to be. Okay, and and he wasn't getting that value. And the attitude wasn't to sort of, circle the wagons around the experiment. He just said, come and have a look. You can tell me what I'm doing wrong. And people did. And they said, why don't you try this? Why don't you try that? Why don't you try that? And he thought of most of these things. But nonetheless, he tried it, and he still got too few. But he was measuring them, but he wasn't getting enough. And so there was a problem. And then physicists were saying, oh, you astronomers can't calculate anything properly. It's the sun after all. But the calculations were okay. And then, I should actually say something. Let me just go back to the Big Bang, that one here. The third part of this PP chain it's a sort of sideshow very much as far as the energy is concerned, but it's where the boron neutrinos, are made, and they're the ones that are the highest energy, and they're the ones that are most detectable. Okay, so let me just go back again here. And so, of course, this then led to neutrino oscillations, which have been predicted by Pontecorvo and others, and also the different flavors that you got, and also the same thing happened in matter with the MSW effect. Again, this was a sort of nice sort of collaboration, if you like, between physics and astronomy, sorting out this story, and you know where we are now. And then, of course, there's the supernova in the Magellanic Clouds, 50 megaparsecs away, seen in 1987. I remember this again, extreme excitement. That's what it looks like now. There's a huge amount of astronomy and astrophysics that goes into explaining this three-wing circus, and I'm not going to go there because it's not a quantum mechanical problem, but it is lovely, and there's a hope that there'll be much more in the way of neutrino astronomy in the future. The current activity is very much concerned not with MEV neutrinos, but with 100 TeV to PeV neutrinos, particularly IceCube at the South Pole, but there are many other facilities. Actually, there are other ones that are doing well. There's going to be watch this space. There's more coming, I'm sure. That's IceCube, but there's more things coming. And then in addition, this is a very good example of multi-messenger astronomy, because one's looking, for example, for neutrinos and gamma rays from the same sources, for example. And here's a gamma ray facility in Western Sichuan, LASSO. It's also, again, another, like this, these are discovery engines. These aren't like the sort of classic physics experiment where you do the theory and then some humble experimentalist goes off and measures what you told them will be there. It's quite the opposite. It's, where did that come from, to quote a famous physicist? And so that's still going on with these PeV neutrinos. And just to give you some one flavor, if you like, of what's actually involved here. There's been a lot of activity trying to associate alleged sources of these neutrinos are real, but the alleged sources, they're getting identified with local sources. In particular, the latest one is a local CFA galaxy called NGC 1068. It's 14 megaparsecs away, and people have been saying that's where the neutrinos are coming from, but that really makes no sense to me, at any rate. I think it makes sense to the people who claim this, but I'll just say that I think this doesn't make so much sense. And the reason why is because there ought to be hundreds of NGC 1068s behind it. You see neutrinos from a Hubble radius away. You see it at the edge of the universe. The volume goes up as R cubed roughly. The inverse square law operates with the flux. So most of the neutrinos ought to be coming from much further away. And to identify them with local sources seems to me very, very strange. But that's what people are doing. And so we'll find out what's going on. The sources of these neutrinos are generally thought to be energetic protons, cosmic rays, which I'll come to in a moment. They're those energetic particles, particularly the cosmic rays, with energies of more than several times a petaelectron volt, hitting either photons or more likely hydrogen atoms, and then making pions and making the neutrinos. That's a sort of generic source, but the environments where these are doing range from corona around black holes to jets coming out of black holes to supernovae to gamma ray bursts, etc. There's a huge amount of discovery there, and it's going to get sorted out. This is in its infancy, and there's going to be a lot more discovery coming of that. I'm sure there's many other neutrino detectors coming online. And of course, hovering behind all this for the cosmology, I'll anticipate this, is the cosmic neutrino background with an effective temperature. It's not thermal, but it's an effective temperature of 1.9 degrees Kelvin. And if any of the students here have a good idea for how to detect this, please come and see me afterwards. I'll help you write it up. Okay. All right. So moving on, in our nuclear astrophysics part, we go on to neutron stars. These were proposed, I suppose, in some sense by Fowler. They were the white dwarfs. The white dwarfs were known observationally since the 19th century, most famously the companion of the star Sirius. Fowler got some of the story, and then Chandrasekhar, as everyone knows and has talked about at great length, made, at the time, somewhat but importantly controversial claims that there was a maximum mass to the white dwarf, and again using the principles of quantum mechanics in a very elemental way, but a very sophisticated way, melding them with general relativity, and in 1931 saying there was a maximum mass. What happens next? Interesting question. Then this moved on in 1932 when Chadwick discovered the neutron, and 2 years later, in a famous actually it was two brief phys-rev contributions. They were very short. Barder and Zwicky. Here's Barder in one of his more contemplative moments, and sorry, Zwicky, excuse me, one of his more contemplative moments, and then they said that they thought there were supernovae. They identified supernovae as astronomers. These were not regular nova exposures, things were much more luminous. They said that they were associated with the acceleration of cosmic rays, which we now believe to be very much the case. And they said these supernovae had to be paired essentially by gravitational energy. The neutron's just been discovered. How about having protons and electrons combined to make a neutral particle and make something 10 kilometers or so across? And that was the sort of idea of a neutron star. Landau is acclaimed to have had similar ideas, but I think explorations of this have not found very good evidence of that. But I don't know. But this was, to say so much in so few words, and to have it not right in detail but right in outline was truly extraordinary. And I think people sort of look with wonder at the imagination that went into getting that story right. Now, we now know that, as I said, the Type 1a supernovae, they're paired by nuclear reactions. And so it is possible to have a supernova made by a nuclear reaction. But the Type 2, it's really gravitational energy that's providing the energy. That goes into neutrinos. The neutrino blow off the ejector and so on. And they give us the display that astronomers that gratify distant optical and infrared astronomers. So what's left behind then is this neutron star, which Oppenheimer and Volkov, using the GR equation of Tolman, were able to describe in 1939. Again, another bold, innovative, because at the same time Oppenheimer and Snyder were thinking about black holes, again, in a way that was much better informed from physics than many of the other things that people were saying. And we now know these are playgrounds for physics. There's almost nothing in physics that doesn't have an expression in a neutron star. It isn't the same thing, it's an adaptation, it's some of it, but almost everything you can think of in condensed matter physics, in superfluid, superconductors, particle physics here, we don't know what the interior is. There's still arguments now about whether or not there are quarks there, whether there are pion condensates there, which would affect the cooling and so on. Astronomers can really weigh in this business because they can measure mechanical things about neutron stars, and they can tell you how hot they are after a certain period of time, which is affected very much by the interior composition, and again, just applying quantum mechanics. One way of which you can do this is to use the, this hasn't quite shown up here, the mass in solar masses against the radius in solar radii, and you can see, kilometers, sorry, this is in kilometers, so that's 10 kilometers, the sort of fiducial radius of a neutron star is 11 kilometers, and there's a maximum mass that depends on the nuclear equation of state. Oppenheimer and Volkov just assumed it was like Chandra did for the electrons, it was essentially a pre-neutron gas. We now know that there are reactions there, as well as this crustal lower density stuff on the outside. And those reactions go into an uncontroversially computed or calculated neutron star radius as a function of mass. And those can be measured. And if you measure a neutron star with a mass, say, of 2.5 or 3 solar masses, there's a maximum mass from the equation of state. Beyond that, it's unstable. And if you exceed that maximum mass, that equation of state has to be wrong. And so where this has got to is that there are confident, well-determined measurements of mass up to 2 solar masses, twice the mass of the sun. There are large error ones that are getting better at round about between 2.5 and 2. And if you start measuring them, as I say, at about 2.5 solar masses, that is very constraining for very interesting cold nuclear physics. Not the Rick type nuclear physics, it's cold nuclear equation of state. And so that's where you can, just a bit over 2 is where you really are with confidence at the moment, but watch this space, there'll be more coming in the not so distant future. That's my fairly confident prediction from NICE and other space missions. Okay, so pulsars, of course, they were the astronomical expression of neutron stars. As observed, they were actually found retrospectively in 1962 in the first X-ray astronomy and identified as such by Riccardo Giacconi, but it was predicted by Shklovsky, I don't think correct, and that is accretion pad, famously, as already been mentioned, 1967, radio pulsars rotation pad, with periods from 1.5 milliseconds to now 76 seconds. This is the longest period that we have so far. There'll be more coming, I'm sure. The Chinese telescope will find us more. Magnetic fields here are 100 megateslas. And of course, the physics is all different here. The atoms on the surface are linear. The Coulomb force is a perturbation to the magnetic force, but they're quantized in a way that you can confidently calculate as an expression of quantum mechanics. And then what's going on in the interior, in the nuclei, and in the lattice is, again, it's now a very active part of discovery and of research. And I'll see why. Here are the magnetic field lines, just a small fraction of the area might be getting out into the outside world, and along those give you the radio pulses that give you the pulses that radio astronomers observe. And here's the Crab Nebula, which is famously part of the story. There's a 33 millisecond pulsar in the middle, a residue of an explosion that happened in AD 1054. And so, and again, I'll come back to this. We're already doing quantum electrodynamics in very strong magnetic fields. We have to solve problems in that environment, and it gets worse very soon. Another object that's very important for our story and involves quantum mechanics is our gamma ray bursts. These were discovered in searches for illicit nuclear explosions in the 1960s, and there were hundreds, perhaps about 300 published papers of explanations for them, not involving illicit nuclear explosions. And we now know, as happens, that there are 3 classes of these things, physically quite distinct. One of the core collapse supernovae, and these make long gamma ray bursts. I'll say no more about those. The short ones, those are the binary neutron star mergers that are the kilonovae, the sources of the other half of the R process elements, we believe. Details to be filled in, but this is the story that's emerged over the last few years. And then there's a third sort, which I'll say no more about. Here, I'll say more about later at the end of this talk, the soft gamma repeaters. And so here's the binary neutron star merger, multi-messenger astronomy, and then we're seeing, again, all these evidence for all these elements from the R process and some S process elements too. So there we go. And now I promised you cosmic rays. Again, I'll say a little bit more here, and then I'll go on. This was a large part of the story of the interface between astrophysics and particle physics. Positron discovered in 1932 in cosmic rays, muons in 36. They were thought to be pions at the time. I think they were called Yukons for a while. But of course, the pion came later in 1947. It's got a shorter half-life, and kaons, V particles, and so on. And the spectrum for the cosmic ray physics goes all the way from solar system particles from 100 MeV all the way up to a third of a ZeV, which is about 50 joules or so. A little bit of uncertainty there, but this is a sort of well-hit cricket ball. Okay, and then this was the heroes who did all this stuff, and cloud chambers and bubble chambers that enabled this. We believe, and I'm not going to say much more about it because this is this is not so much quantum mechanics at this point. I'll just say a bit later at the end about the extragalactic component. But these all come from supernovae, so Barton's wiki we now believe are quite correct. This is diffusive shock acceleration from the supernova explosions. Then there's the shin of the spectrum, if you like. There's sort of various knees there, and then the shin of the spectrum. Maybe pulsars. I think there are actually also shocks personally. And then out here's the extragalactic component, which I'll say a little bit about at the end. Then it'd be remiss of me, although it doesn't quite fit into the story that I've been telling, not to mention Hawking radiation, which again is quantum mechanics, this time applying quantum mechanic principles in a very subtle way to the classical gravitational field, Stephen Hawking and Jacob Bekenstein, and the connection with the entropy and the area, which has to increase like entropy, and then the idea that if there were any of these primordial black holes made in ways that I don't understand for sure in the early universe, if they were less than, say, a petagram, they would evaporate over a Hubble time. And then this has really birthed a huge amount of febrile imaginations of theoretical physicists have known no bounds in going off into thinking about information paradoxes, unitarity, firewalls, wormholes, and so on. Observed from a safe distance, I think this is in better shape than it was when my colleagues in the next building were almost at one another trying to sort all this stuff out, but it's now in better storage, and so it's a birth in some sense, this. And then the primordial black holes, I've been a little bit involved in some of the upper limits and searches for these. There's no evidence for any of them, but it doesn't stop them being terribly important for ways of thinking about quantum mechanics. So let me just move on. Now I go on to cosmology. Again, I can only say a little bit about an enormous subject, and I suspect it's quite familiar to much of the audience. One of the big puzzles is baryogenesis. And I'm doing these in no order. We know in the standard model of cosmology, which is well substantiated, that the baryon to photon ratio is 6 times 10 to the minus 10. And the question is why? Why isn't it 0? Sakharov thought about this, and he came up with 3 conditions, which I've just listed here. Again, I think this is all fairly familiar, and they can be satisfied by some versions of theoretical particle physics interactions. Certainly there are precedents in existing measurements in experiments for this, and the thermal equilibrium is the thing that thermal disequilibrium happens quite naturally in the expanding universe, and somehow or other this has left us with that. Could be leptons that are doing the story, but most people believe it's baryons. Again, a really great puzzle for to be solved is to understand baryogenesis. Then the one that has caught the most attention of all is dark matter. This, of course, has been around since the 1930s. Fritz Zwicky, yet again. Vera Rubin, after which the Vera Rubin telescope, which we hope is going to be delivering data in a year or so, is named. He for clusters of galaxies, she and actually others, but especially her for galaxies. And then cosmology needs and measures this dark matter, and it's as dumb as you can get. This dark matter, it does nothing except gravity. And there's no evidence for anything else, and people have been trying to do it. What is it? Well, the investigations have gone from yocto-electron volts to million solar mass black holes and beyond. These are the proposals that are out there. I can find you scholarly references on this. So we've really making progress on the mass. We've got it down to 90 orders of magnitude. Now, in practice, of course, as I think you heard in an earlier talk, there are a lot of exclusions. Some of them are astronomical. Some of them are measurement, direct measurement, and some of them are just plain common sense. And some of them come from how do we get all the microwave background fluctuations right if we're doing your crazy theory here. So there's a lot of exclusions there. And then, of course, there are searches underground. This is just one of them. And you can see the exclusions with the WIMP mass and the essentially the cross section. You can do them on ground at accelerators, supersymmetry and so on, and above ground with space telescopes, especially Fermi Gamma Ray Space Telescope, which set very good upper limits, in my view, on finding the results of dark matter decays and so on. So very much a work in progress. One of the very best problems in physical science is to identify dark matter that you can do with the confidence that it's there. It's not something that may be there. Then there's the primordial fluctuations. How are we doing for time? I think we'll be okay. Primordial fluctuations, again, this is fairly well known. The standard model of cosmology is brilliantly successful. There are some tensions. I'm personally not losing a lot of sleep over them. People whose funding depends on there being tensions lose more sleep over them. And it's sort of a successful story, but then it hasn't told us about the fluctuations, and that requires a sort of version of Hawking radiation. I'm oversimplifying considerably here. A quantum origin during inflation, and which is sort of required. I can say more. I won't say any more about that here. And the simplest thing is just scale free and a small tilt, and then that gets elaborated in various ways, which again, I haven't got time for, and you've heard about, and it's in the simplest version, it's expected to be Gaussian. So there's a sort of prediction here on the basis, on an Occamist perspective. And again, it's been brilliantly substantiated by the observations of the microwave background. If you look at the corresponding large-scale structure, I would be a little more skeptical about these alleged tensions here. And the reason why, I've got it, 5 minutes, thank you. The reason why I'm skeptical, and I speak here as an astronomer, if you're working with elementary particles, you've seen one electron, you've seen all the electrons. I mean, they're all the same. If you looking at galaxies, if you've seen one galaxy, you've seen one galaxy. The most cursory examination of galaxies through a telescope says everyone is different. I say they're even more diverse than people. And so if we're going to use effective field theory, great for doing it for an elementary particle. Be careful with doing it for galaxies. See if you can make it work in sociology first. And so, because it's, the dark matter may well be described by this, but the tracers are the galaxies, and they have their own peculiar idiosyncratic ways, the way that they are born, marry, and die. And they're all different, and so that's why I'm not so fussed about these sort of tensions in the large-scale structure. But we'll find out. We're going to learn a lot more. There's big redshift surveys coming, and we're going to learn a lot more. Okay, I said I'd finish with 3 topics. I think I've got about 2 minutes for each of them, less than that, actually. So again, these are just, I'll just sort of put them on the table here. The first one is, and I'm just tribute to Michael Berry, who talked about the ghost in the machine last night. And of course, it's terribly important. Backing up a little bit from that and just taking an engineering view of the origin of life, that in lots of experiments carried out in the primordial Earth, for example, there are molecules that are developing. And the thing is, there's one chiral system, and that's observed. Everything we've seen in this living has one chiral system. Is this chance, or was there some War of the Worlds, for example, or is this a causal connection? My colleague and I have explored the possibility that there's a causal connection here, and it's the cosmic rays that are responsible for imprinting a tiny bias, just like in baryogenesis, and it's the muons that, there's one every few there's a muon going through your body every few milliseconds. I apologize, but as a cosmic ray physicist, but I'm sorry about it, this violation, but there is one going through your body about every 2 milliseconds or so. And this tiny bias, if this is right, I think the explanation has to be quantum mechanical, and I've been particularly interested in listening to the quantum error correction stories yesterday, and my mind has been fantasizing about ways of thinking about that in this context. In order to, there are various things that one can look for, and I'm actually involved in some experiments using circular polarization and muon accelerators to actually put biological materials in them and see what happens. The precedents for electrons experiments are very, very good. Okay, the second thing is, I said the third type of gamma ray burst, the soft gamma repeater, this has been identified with magnetars, and these magnetars are neutron stars, almost certainly very young neutron stars, maybe a century or so old, no much older than us. 2 minutes, I've got it. And they are, and they're characterized by being slowly rotating, but having magnetic fields as high as 100 gigatesla. That's 30 times the Schwinger field. So quantum electrodynamics is vaulted into a completely new regime, many-body regime, and many of us are working on trying to understand this. It could be even 2 orders of magnitude larger in the interior of the star, and lots of exotic possibilities there, and lots of observations to start seeing some effects that may be telling us the answers to what's actually going on. This is all very exciting. Big discovery has been the fast radio bursts. These happen about 1 minute over the whole sky. They have effective temperatures about like that of a tsunami, 10 to the 40 degrees Kelvin. And I won't say you anything about that, but they involve stimulated Raman scattering. This is the plasma physics version of Rajaram's Raman scattering. And there's a lot going on in this area, and big telescopes being produced to look for them. And then the final thing I'll say is the ultra-high energy cosmic rays. This again is something that's very exciting, is understanding what's going on here. And here there are puzzles in understanding the SHAS. It goes to hundreds of times the center of mass energy of the Large Hadron Collider. And really, in order to make further progress and identify the sources and see if there's, we now pretty strongly believe the highest energy ones are in fact iron, not protons. In order to identify the sources and so on, we need better data for interpreting the SHAS, and that has to come from modeling, from extrapolation of the LHC data, and from theoretical physics and so on, and explain the muon puzzle and so on, so that individual SHAS can be identified in terms of energy, nucleus, and direction. That's the way we're going to make progress. So this is the challenge to quantum mechanics, is to help us with that problem. And here's my final slide. It's a summary. This is more as to what I said. A couple of parenthetic things I was going to make at the end, but I will stop at this point as my time is just, there's a flashing red light. I don't know what happens next if I go beyond that. So thank you very much indeed.
Thank you for a wonderful run through the connection between astrophysics and quantum mechanics over the century. Questions, Rajesh? Then, you have the mic.
Thank you very much for a. This is not on. It is on. It is on. Thank you for a very wonderful overview. I was wondering why no mention was made of the Saha ionization formula, which was one of the earliest. The Saha.
Yes. Oh, yes. So I should.
The earliest application.
That's an omission on my part. His picture should have been up there. Yes, it certainly should. This was a huge. In fact, somebody was telling me about Saha. He left science to do something different afterwards. I can't remember who told me that here, but yes, that was a huge step. Absolutely.
And the other one was the negative ion of the hydrogen.
Yes. No, I did. I mentioned that. That was Chandra. That was Chandra. I did mention that one. I got that one. Okay.
Thank you.
Rajesh.
Thanks, Roger. That was so terrific. Maybe you mentioned it, but what was the origin of this very strong magnetic field in these magnetars? I mean, you said 100 teratesla or something.
Yes.
Do people understand how you can generate such high magnetic fields?
Well, as often happens in astrophysics and indeed particle physics at this stage, yes, many people understand. It's just they don't agree with one another. So yes, the simplest thing to say, which is almost certainly not helpful, is you just have flux freezing and collapsing conducting plasma to make the neutron star, and you can accumulate 10 to the 11 Tesla that way. Okay. The more the more likely thing to happen. These are hot, turbulent environments, and you'll get some overturning going on. Dynamo processes are happening in the nascent neutron star. I would put my money on that. But turbulence is hard with fluids. It's the problem, as most people know, Heisenberg worked up and gave up on and then took the soft option and invented quantum mechanics. And it's harder with magnetic fields. It's even harder with exotic post-plasma processes around magnetic fields. So it's even worse. So that's going to be a long time coming to understand it, but I would say that's where one should look for it. It's not unreasonable that you make fields this strong. They're still not dynamical at that strength. 100 times more field, and then it becomes effects equation state.
And just a quick follow-up to that. So what would be the very striking experimental signatures of astronomical signatures of this strong QED, this Schwinger regime?
Well, there are many things that are going on. Firstly, it's the observations from the surface. There are X-ray observations from the surface. The second thing is the fast radio bursts. And these are millisecond or so pulses. They're probably microsecond in origin. Big telescopes are being developed to identify them and examine them in detail. Three of them, but particularly one of them, has already shown periodicity. So you could be looking at evidence of normal modes of vibration in the surface of the star, just like astroseismology and helioseismology. You could be doing it with neutron stars. The late Mal Ruderman used to call this discipline astrology. You could be looking at a sequence of observations of pulsations, which would be then very prescriptive of what's going on below the surface of the neutron star. There's certainly one well-determined, I think, periodicity so far, but whether or not this is a fluke remains to be seen. There's a lot more that's being found. Some of them have structure even less than a microsecond. So this is very prescriptive for the origin of these fast radio bursts. The low frequency things, they're just seen in radio astronomy. And they're like I think they're like tsunamis and should be treated as such. In fact, if you allow me another sort of old man's rant, I think, I'm a great believer in using reductionist physics most of the time when one has to, and physicists do that. But if you're doing things like turbulence or doing things like tsunamis, you don't investigate the private lives of water molecules. Curiosity about that. You do equations of momentum conservation, energy conservation, and mass conservation, and so on. And that's what oceanographers do. And I think that's the way to look at these radio bursts. But even then, it is prescriptive at that classical level for what's going on in the surface. And I think that's going to be our route down beneath the surface.
Let's move to Sai.
Hi. Thank you, Professor, for the very nice talk. Just a quick question. I'm also very impressed by this large numbers, the magnetic fields, the 100 teratesla and so on and so forth. So could I ask a more simple question, which is how does one actually estimate this number? Because it would saturate any detector that we could ever conceive of building. So I imagine that this is an indirect measurement.
Oh yes, so
so could I just ask, A, how does one estimate it right now? And B, how well would one like to estimate it to investigate the kinds of questions that you've brought up? Is there a gap here?
There's not enough time to give a full answer. Let me say the icon at the start of this was the Simon's collaboration, the extreme electrodynamics of compact sources, a palindromic international collaboration. We look at these problems very much. So this is very much on my mind. My colleagues who are in this collaboration, Chris Thompson and also Rob Duncan, they made a very bold prediction, a bit like Barton's Wiki and all of that there were these 10 to the 15 Gauss or 10 to the 11 Tesla magnetic fields around a subset of neutron stars, and they've turned out to be brilliantly corroborated. Their reasons were basically to do with radiative transfer, and the corroboration came from dynamics. We can figure out how rapidly they should slow down. and it's consistent with these very large magnetic fields. These magnetars are magnetically paired, not gravitationally paired, not rotation paired, they're magnetically paired. And that's how you see it. How you go further is you do the detailed quantum electrodynamics. I was doing this sort of stuff a little bit in the primitive level in the 1970s with Ted Charleman. Now it's quite a sophisticated business. We're not saying quantum electrodynamics is all wrong at these levels, but what we are saying is it's a lot more complicated. And those of you who are in the eternal quest for new physics, this is as good a place as any to look. But as in cosmology, I'm a reluctant conservative in the sense that I believe the simplest explanations and the most prosaic, and hope I'm wrong.
Thank you.
Okay. I had one question, if there are no other questions. You mentioned that the origin of fluctuations is quantum.
Yes.
That's, of course, a great connection, but it translates to classical. This transition of quantum fluctuations to classical, is that a problem that you think is a forefront problem, or you think it's understood in cosmology?
Oh, gosh. Well, I think firstly, I mean, okay, my view, and I think it's not an uncommon view of inflation, is the simplest assumptions you can make led to a set of series of corroborations. Insofar as we have reliable observations, they have been corroborated. Right. Had it been worked out observationally to be totally different, it would not have required much imagination. In fact, it was already in the literature, a whole slew of alternatives that could have been called upon to explain it. But the simplest thing does seem to work, just like it is for the expansion of the universe overall. The simplest thing, almost the simplest thing, because we've got cosmological constant, almost the simplest thing does seem to work. So, but having said that, there are genuine puzzles. Firstly, with, say, reheating, for example, is a puzzle, and what this does to this. Then I think, as a practical matter, I think the biggest puzzle is translating the fluctuations, which are primarily in the dark matter and corroborated by the observations of the microwave background, to say what that tells you about a tiny fraction of the mass, which is in the form of baryons, and a tiny fraction of that getting into galaxies, behaving in this idiosyncratic, personal, just look at me way, which, when you've got billions of these things that are catalogued by astronomers, you've got to go from their catalogues to something about the early universe. There's, that could be much more complicated, and we should be humbled by the scope of that problem.
Okay. Was there any other question? If not, let's thank Professor Blandford for an amazing talk. Thank you.